So welcome back. I want to tell you full disclosure, I'm a little bit frazzled this morning. I feel like I've had a crazy morning, so bear with me here. I don't even have time to tuck my shirt in. Thank you. Stand behind this podium so you can't see. Let me see here, where are we at? Oh, so we didn't have class Wednesday, we had the wellness day, and so homework is due this evening. I passed test 2 back on, I don't know, Tuesday or Wednesday, so be sure to look at those grades. And you know, there's solutions as part of the Gradescope thing I returned, but I will also post solutions to Blackboard as well. But you have the solutions, so just be aware that they're out there. Let me know if you have some questions about that. I know there are a lot of questions about optimization, and so I had like, I think 4 or 5 questions that I wanted to at least help you get started with before we get going here. And let's see, at the end of class, we'll have our short quiz. So, you know, just be aware of what's going on in terms of homework though, right? So there's 1 homework due tonight. Always surprised at how few people start that one for the day it's due, but you guys do you. Help you get started with that. And there's 2 due next week, 2 due on Wednesday. So there's a lot going on. We'll have our quiz today. Let's get started. Anything you want to talk about before we get started? Anything not related to those things I just mentioned? All right. For those of you folks who are doing this remotely, you know, more and more folks keep moving remotely without telling me, which is interesting to think about. Could you at least turn your cameras on and pretend like you're in class? That would be great. All right, these are the questions I had questions on. So people sent me some emails. People were interested in looking at 2, 4, 6. This is number 7. Doesn't have a number, but it's number 7 and 8. And I'm not gonna like do all of them, but I'll help us get started and help us think about how we can at least start these problems. And you can let me know if there's more you want to look at moving forward. I know like a decent number of people haven't started these, so I don't want to go too far into them. So on this first one, the reason this first one's confusing is because it's got a lot of variables in there. So this equation, like it says in the problem, it tells us the speed at which a fish swims. And so V is the speed, right? Relative to a bunch of other inputs, right? So it's got, let's see, it's got L, which is the distance. It's got U, which is something that I'm not seeing the definition of. The current, is that right? Yeah, so I guess it's the current. But I think the confusing thing in this is what do you actually do? Because it's all variables, right? And so the question says, I'll get my notes out on this so I don't lose track of what I'm talking about. It wants us to do, wants us to take a V derivative, because you can see V is the variable, and it also wants to know determine the value of V that minimizes E, right? So this is telling us to take a V derivative of E, and then we will set E prime equal to 0 to find the critical points. Right, and then we'll figure out which is a min. Although, yeah, we should make that. And we'll classify them. And so again, I think the confusing thing in this is there's no numbers other than the cube and the exponent. And so that's usually what trips people up on this. And the thing that is kind of key, which is a little bit related to what we're doing in class today, but only tangentially, is if we were going to take the V derivative of some non-V variable like X, for example, we treat it as a constant. So when you write d over dv, it says, hey, the variable's V, and we're going to differentiate V. And so if you're differentiating X with respect to V, it just becomes 0 because it's like treating it like a constant. In other words, it's not a V, And so you don't apply the derivative rules, you instead apply the constant rules to that one. And so, you know, the derivative of x would be 0 in that case, or let's say we had an example like we wanted to take the derivative with respect to t. Should I do t? Yeah, let's do t of like 2x y t squared, right? So there's a bunch of variables in there. There's also a number, but we're differentiating with respect to t specifically, right? If we're doing that, we ignore the 2, the x, and the y, and we just differentiate the t part, because that's the variable we're being told to differentiate, right? So this is kind of extending this to future classes a little bit, getting us to ignore the things we're not differentiating, right? So if we differentiated just the t part, this would become 2xy times 2t, right? And then we can multiply the 2's and get 4xyt, if you catch my drift there. And oops, so that's the kind of thing we want to be thinking about in this problem. When we differentiate with respect to v, we're going to ignore the things that are not a v. And we're just going to pretend like there's a number in there. So that's my general setup. I'll do a little bit of this one at least. Maybe we could do the whole thing. I don't know. Should we do the whole thing? I don't know. Let's start it at least. Are there questions about what I'm trying to say? Sort of the setup. Okay. So I'm going to add another page here just so we don't run out of room. Let me rewrite this problem. So the problem is E equals AV cubed L over V minus U. So I just took the thing that was out front and I put it in the numerator. Is that okay? Everyone see that? This thing is multiplying and it just goes into the numerator. And so it becomes this. And I wanted to do that because now it's a quotient rule. Before it would have been like a product rule and a quotient rule. And so we're going to do d over dv, and we're going to treat a, l, and u like constants. And if it helps, you could just put numbers in there if you wanted to, and then maybe it's less confusing. But then when we do that, when we think about it like that, and we do d over dv of e, it's going to be a quotient rule. Right? And maybe I'll at least write down the first step here. You can let me know if you want to see more, but when we do the quotient rule, right, that it becomes this. F prime, how much detail do you want to see? F prime G, right? So see how I differentiated this thing only into this and the 3? Right? I ignored the A and the L. I just brought down the power, subtracted 1 off the power. So that would be the numerator, F prime G minus F. And then G prime is just a 1 because we're only differentiating the V. How's that derivative look? I feel like that's the most confusing part here. We're treating everything like a constant except the V. So maybe I'll leave those highlights, right? So this thing turned into this and this. And then this thing just turned into the number 1. And the U just went away because it was a constant and it became 0, right? Should I say some more about that? We'll see what's going on there. Okay, maybe just in the interest of algebra, I'll take it a couple steps further. So we want this to equal 0 because we're trying to find the critical points, right? And so we take the numerator and we set that equal to 0. And so we do the numerator equal to 0 because it's a fraction. And the numerator ends up simplifying in these kind of steps. It ends up being, how many steps should we show here? So I'll just say after simplifying, it becomes 2ALV cubed minus 3ALUV squared. And we were solving for V, right? So how do we solve something like this if we're trying to get V by itself, right? I'm highlighting the two places where V is located in that expression. What would you think about doing? We've seen a bunch of problems that look similar to this. Don't let the extra things confuse you. Those are just like coefficients. Right? If you had numbers in there, it'd just be like something V cubed minus something else V squared, right? Thoughts? What should we do when you see those two terms like that? So these two things are being subtracted, so we can't combine them because they're not like terms, right? This is a V cubed, this is a V squared. The thing I'm trying to point out is if we want to get V by itself, you can factor out a V squared. Right, again, we're trying to solve for V here. And so that was helpful because now the inside piece only has one V. Right, we still want this to be 0, so equals 0. And so we can just set those things equal to 0 separately. Actually, I could have factored more out, right? I could have factored an A and an L as well if I wanted to. It's not super important though, so I'm just gonna leave it like this. Right, so this one could be 0, so we get V equals 0, that's a critical point. Or this piece equals 0. Right, if you want to get V by itself, just divide that other stuff over to the other side, except this should be a U, just to be clear. This is a U. And so V equals 3ALU over 2AL. The A's and the L's cancel. And we just get 3/2 U. Or you could write it as 3U over 2 if you want. So this is the other critical point. Trying to read the problem again. Minimize the energy. Yeah, it's not super. Anyway, questions before I say something else? We got those numbers? That's a U. My U's are terrible right now. That's a 3U over 2. So what's the answer? The answer was, or the question was, what value of V minimizes energy? And so the question is, which is the min? How do we figure that out?
A test.
Yeah, so we could either use A, either the first or second derivative test. Although to be perfectly honest, that's going to be a little tricky because we don't have a lot of numbers in here. And so maybe we could plug numbers in to the derivative and get some values. But I think we can probably just reason which one of those makes the most sense. And I was trying to, I wrote in my notes that V equals 0, this one right here, violates the constraints. Because if we look at the problem, this I think is the key thing here, which is that U has to be less than V. And U is some non-negative thing, right? So V has to be positive then. right? And so this can't be possible because it's not positive. Right, the fish is swimming, and so if it's swimming, its speed can't be 0. That's another way to sort of think about it. So first derivative, second derivative test is fine. That's a good way to think about it. Although I just, full disclosure, it's going to be tricky, or just use reasoning about constraints. All right, so we pretty much finished that one off. So this is going to be the min. And I think everyone has that same value, that same problem. So it's not like you have to do something different. Thoughts about that one? Clarify anything that we did there? That one took a while, which is fine. You know, looking back at my past notes, I ended up spending a class or period or so in my past classes, like looking at these problems. So I have no problem doing that today. Are there questions about this one though? Okay, I'm probably not going to do the next one, but we can set it up. And maybe I would be asking whoever asked this question to maybe clarify what it is confusing about it. So let's read this one. So we've got a civil engineer. They want to estimate the maximum number of cars that can be on a road at a given speed. They're assuming that each car is 20 feet long. Sounds like a constraint. Travels at a speed of s and follows the car in front of it at a safe distance for that speed. I don't know if that's relevant, but okay. He finds that number n of cars, so n is the number of cars, that can pass a given spot per minute is modeled by this function, right? So n is the number of cars and s is speed. And the question is, what speed can the greatest number of cars travel safely on the road? How do we want to do that? What's this asking mathematically? What's this say? What's this saying? Anyone? Anyone do this one? Gregor?
So it's asking for the maximum number of cars that can travel safely.
Yeah, so how do we do that mathematically?
Find a critical point.
Yeah, so we're going to look at n prime, set it equal to 0, find the critical points. Did you ask this one, Gregor? I can't remember.
Yeah, I did.
So yeah, what was the answer?
Setting it up, but now that I look at it, it's pretty.
Okay. Yeah, I would categorize this in one of the easier categories. None of these are easy. I want to be clear, right? This is finding critical points of a rational function that has fractions in it. So like, there's definitely confusing aspects of it where, you know, we've been building up to this kind of, it's kind of the peak of, you know, critical point finding, but it is kind of sort of a quote unquote straightforward rational function. And I would encourage you, if you're struggling with finding the derivative and you're wondering whether that's hanging you up, you can always just go to something like wolframalpha.com, or if you just put it into Google, like type this function into Google and say derivative, you can always verify your answer that way. You obviously want to be able to do it by hand, but if you're just concerned that that might be the problem, that's a good way to check. So maybe I won't do this one if that seems okay. I think the next one's kind of similar, so we can look at that one too. Is that okay? Okay. So the next one, no, that's not the one I was thinking of. So the next three, I guess, they're all of the type where you need to make the equation ourselves, right? So maybe I'll just open up the notes real quick and remind ourselves how to do that. So we're thinking about these steps, right? Defining the variables, drawing a picture, coming up with the objective function. Those are usually the three things I try to do together. So let's do those first three steps of, nope, this problem, nope, this problem. And then we can see if we want to keep going or not. So this is similar to the example we did, right? So a guy's building a fence. We did an example like that in class. The difference between this one is that it's a different shape, right? So the ramp chair has a certain number of square feet, that it wants to enclose. And they're describing what it looks like, right? So it's a rectangular field, but divided in a half with a fence down the middle. And so let's draw a picture of what that looks like. Maybe like that. Although it's not clear if the line's supposed to be like that or like this, I guess. But I don't think it really matters. But the key thing is that it's rectangular, right? So if we start labeling things, we know like the three things going down the middle are the same size, for example. So we can label like X, 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 for example. And then the sides might be Y, Y, or something like that. And so we could say like, maybe I should move this up to the top. Oops, I moved my highlight as well. That's okay. So we can say, what were you going to say? I was going to say X is the width, Y is the length, and the objective function is to minimize the total amount of fencing, right? Subject to some constraints. So what's the total fencing? Looking at the variables we have, what's the total fencing?
2 million square feet.
So that's the area. So someone online said 2 million square feet. The 2 million? 22 million, yeah. So we want the area to be 2 million. But the total fencing is like a perimeter thing, right? So we want to minimize the total fencing, which is 3 X's and 2 Y's. Really needs to be clear that that's what we're trying to do here, right? Total fencing, minimize it, whatever it says, whenever it says minimize or maximize this or find the most or find the least, that's the objective function, right? So when it says minimize blank or maximize blank, that's the thing we want to be writing down. So minimize total fencing. Okay, I'm looking at my picture. What's the total fencing? Well, there's 3 X sides and 2 Y sides. So that's how I got 3X plus 2Y. Is that okay? The 2,000 square feet part is the constraint. And so we want to minimize that value. Okay, well, what's the minimum value of that? 0 is the minimum value of that. If you have 0X and 0Y, that's as small as that could be. Or if you made them negative, it'd be even smaller, right? But when we put it in context, that's when it starts mattering. So we don't just want this to be small. We want it to be small while being 2 million square feet. And so that's the constraint. You need 2 million square feet of fencing, right? And so what's the area of this thing? This is an area formula. In terms of the X's and Y's, what's the area of that enclosure?
Y times X.
YX, yeah, base times height. Right, and so we need X times Y to be 2,000 or 2 million, excuse me. 1, 2, 3, 4, 5, 6. Right, the constraint is how we get rid of the variable that we don't want to be dealing with. Because currently, if we were going to try to find the minimum of this fencing equation, it's got an X and a Y. We don't know how to differentiate things with X's and Y's. So we use this relationship to get rid of one of those variables. Remember how that worked in those examples? Just to kind of flash back to the notes. Right, we did that. Let me just look at the fencing example we did. Right here is a fencing example. We had a similar thing where, hey, we want to find the max of this thing, but it's got an L and a W. And so we look at the constraint, solve for the constraint, and then rewrite the thing that we wanted with just one variable. And so we're going to do the same thing here. It's just a different formula for the area, for the objective function, and it's a different constraint, but it's the same idea. So, going back to this example then, we want to take x times y equals 2 million and use that to substitute out one of the things from here. Right? So this thing is going to rely on this equation in this way. We could say, it doesn't matter which one we do, we could say y equals 2 million over x. Or you could do x equals 2 million over y, right? Really doesn't matter. But then you take that value and you plug it back into the equation. So we know we want to minimize 3x plus 2y, and I know that this equals y. Right? And now it's something that only has one variable, and we can find the minimum of that. So I would like you to finish that one. I don't really think I want to do it for you, but I think it's similar to one of the ones we looked at. Thank you. What is it similar to? It's similar to solving the equation that comes out of there is going to be similar to solving this equation. Right? It kind of looks like this. Because you have a t in the bottom and the t in the top. Right, we have that right here because you got an x in the bottom and an x in top. So it's going to be similar to this, to solving from that equation. So you can follow along with that one is what I'm trying to say. The setup's the important part. If this is a test and you got this far, you get most of the points. So can I clarify something about it? Okay. I will put these all in the drive, of course, to get you, so you can reference them later. Come on. Okay, this is number 7. I forgot to screenshot the number. Actually, oops, someone asked a question. So then we would take the bottom equation in green. Let me go back. For some reason, my pencil is having some issues here. Geez, okay, sorry. So we take the equation in the bottom in green, set it equal to 0, and find the min. No, that's not how we find minimums. How do we find minimums? We take the derivative, we set that equal to 0. That tells us the critical points. Then we classify the critical points. Right, similar to the one we just did a second ago, or this one here. Right, we took a derivative, we set it equal to 0, we found the critical points. Okay, let's keep going. Let's set this one up. Love this one. But this one looks really complicated, but they're actually just trying to like walk you through it step by step and not just, like the last one was just do the whole thing and then tell me the answer. This one is first write down the constraint, write down the objective function, substitute them. So it's getting you to do it step by step. So don't be scared of this one. And it's an interesting problem, right? So it's saying, okay, US postal regulations, here's a hypothetical package. The girth plus the length can't exceed 108. And then it tells us the girth is the smallest perimeter of the smallest side, I mean. So what that means is, if this is our package, what's girth in terms of those variables? It's the perimeter of the smallest side. So X is the smallest side. What's the perimeter of that side? 4X, right? There's 4 sides on that small side, right? The perimeter of the smallest side. And so what this says is girth what is it? Girth plus length can't exceed 108. Let me make sure I don't miss anything. I did this one ahead of time just to make sure it's good. Yes, okay. So, oh, it's walking us through it though. So let's just do it step by step. The first question says, what's the formula for the volume? Oh, because the question is, what dimensions maximize the volume, right? And so if we want to know the dimensions that maximize volume, we should write down the volume equation. What's the volume of this thing? How do you do the volume of a 3D thing, you know? Yeah, you multiply all the dimensions together, right? So it'd be x times y, or x squared y, right? That's the volume of this thing. So that's our objective function. But okay, ultimately we want to be able to figure that out without it walking us through it like this, but hopefully that makes sense, right? We want to find the largest volume, so that's volume. And then it says, okay, well, we can't find, we're going to minimize this in a second, or the maximize it, I mean. But like it says right here, the problems tells us that the parcel's length plus girth can't be more than 108. And so if we want to maximize volume, like it says, I'm just reading this paragraph. If we want to maximize volume, we assume that we actually need the girth plus length to equal 108, right? So it has to be less than that, but we want the volume to be as big as possible. Let's hit the biggest mark, right? So what is the relationship that represents that? So we want girth plus length to equal 108. And so that means girth, which is 4x, plus length, which is y, has to be 108. And so that's our constraint. Are there any other constraints? There are other constraints. What are the other constraints that may help us later? Y has to be not negative. What else can't be negative? X, right? We can't have a non-existent box. We want a box. If they were 0, we wouldn't have a box. If they were negative, we'd be in some alternate dimension or something. So we need to have positive numbers. And this is helpful because if we get a bunch of critical points and some of them are negative, just forget about them, right? That's why that's helpful to kind of check that with your understanding. Okay, and then it's saying, okay, well, let's solve this in terms of y. And so just subtract 4x to the other side. And then it wants you to substitute it into the volume equation, right? So we used to have x squared y, but what we just did is we solved this for y. And so we can take this piece and put it into the y, right? And then it would be x squared times 108 minus 4x. And we want to find the max of that. And so that would be a product rule, right? If we took the derivative of x squared times 108 minus 4x, this would be a product rule. Can we do something to make it easier than a product rule? Yeah, just send that x squared through and write it as 108x squared minus 4x cubed, and then it's just a power rule. Right, so just that kind of thought process saved us. The product rule wouldn't have been horrible, but now it's just an easy power rule, right? And we're going to find the max, or you're going to find the max. Sort of the question before that involves doing v prime equal to 0, classifying the points. What do you think? Anything at all? Anything I can clarify there at all? Feel okay finishing that one? Okay, I think the last one is the hardest one. And it's the hardest one because it involves some trig stuff. Or at least some triangle things. Anyway, this is definitely the hardest one. I'd like to at least, we'll set up the objective function again. Let's just at least do that. And this is one that a picture would be really, really helpful for. So a fence, which is 3 feet tall, runs parallel to a building 4 feet away from the building. Let's draw that picture first. So we've got a building. I'm going to draw the picture down here, and then I'm probably going to go over to another page. So we've got some building, and it's parallel to a fence that's 6 feet tall. This is my fence. And it says it's 4 feet from the building. And we want to take, this is like a super classic problem, by the way. I don't know if you've ever seen one of these before, but pretty much every single optimization textbook has a problem like this. And so we want to put a ladder against the building that gets over top of the fence, right? So we want to do something like this, where this is my ladder. And the question is, what's the length of the shortest ladder that will reach the ground, that will get over the fence to the building, right? Because if the ladder is too small, it's going to hit the fence is the idea. What's beyond that setup? So, you know, when you see problems like this, it should be just screaming right triangle kind of things, right? We're making a triangle kind of shape there, and it's actually 2 triangles. So if I simplify this picture a little bit, it really looks like this. Right? We've got a right angle here and here. We want this side length. We want to minimize this side length L, and we know these 2 dimensions. I'm going to continue to label this, so I'm going to move it over here a little bit. And so let's call the length of the bottom triangle X, and maybe I'll move this one so it's a little more clear. And so if we want to know the length of the entire bottom, that's not what I wanted. What's the length of the whole bottom of that triangle? X plus 6. Okay, that's a good setup. I'm going to label the height of the building Y. Does the picture look okay? Add another page here.
Are the dimensions the same as in the problem?
Yeah, I think so. They're going to be different. So the one I pulled up had 6 and 4. Oh, it's supposed to be 4. I'm sorry. That's what you're saying. Sorry about that. Does everyone see that? Those 6s should be 4s. They're actually, you know what I'm going to do? I'm going to change that 4 to a 6. Everyone has different numbers. Does everyone see that? I'm just changing this number to number 6 just so it matches up with the diagram I just drew. Okay, does that seem okay? All right, so anytime you have a right triangle, there's 2 things that come up a lot. There's 3 things that come up a lot. either SOHCAHTOA, a squared plus b squared equals c squared, right? Pythagorean theorem. And the third is similar triangles. Are you familiar with similar triangles? If you have something that looks like this, like the situation we have, it's like you have a big triangle and then there's a little triangle inside of it, right? And if they're labeled like this, let's say let me just zoom in on this triangle. If this one is labeled A and the whole thing is D, and let's say E, B, then this relationship is true. You can compare sides in the big triangle and then compare sides to the little triangle. For example, you can write something like E is to A as B is to D. This is called similar triangles. And to be perfectly honest, this is the kind of thing that I needed a refresher on when I started teaching this stuff, because it's been so long since I've seen it before. You remember that kind of thing? So E and A, notice E and A, like E is the same. What I'm trying to point out here is E and B are kind of like the same side lengths. They're the same sides, right? They're both like the right-hand side of the triangle. And then A and D are both the bases. And so that's what lets us compare them like that. You're comparing the same right side to the bases. Does this ring a bell at all to people? Or is anyone like, yeah, it's like a high school, it's a thing that you learn, I think, in a full-on trig class, although it's been a while. And it's not the kind of thing I review in pre-calc if you've had pre-calc with me. So anyway, those are the three things that always come up with the right triangles. And so I just wanted to write the three things down. And we're going to use two of them in this problem. Because we want to be able to relate the sides, because that's how we're going to maximize or minimize something, right? And then we have some constraints. We have constraints like we needed to get over the building, right? We want to maximize the ladder. So we have these things that we want to make happen. So that's sort of the general setup. I'm going to keep going with it, but are there questions about the triangle stuff? Check my time here. Okay. So seem okay? All right, so we want to minimize, right? Minimize. What is the length of the shortest ladder? And so our objective function then, we want the shortest ladder. And so what is ladder? What's the equation for ladder based on our picture? Yeah, we want to use the Pythagorean theorem. So we want to minimize the ladder. And the ladder, looking at the picture on the top there on the second page, or on the first page, I mean, is a squared plus b squared equals c squared. So it's y squared plus x plus 6 squared. All right, this is Pythagorean theorem. You don't have to, but it might help later. At this point, we're not ready to do any derivatives though, because it's got an x and a y. Oops. Right, we have an x and a y, and so we need to get rid of one of those as the next step. And that's where the similar triangle thing comes in. So let me clarify that and see if there are questions. This is the only thing we're doing today, just by the way. We're just gonna work through this, hopefully make it make some sense. I'm happy to give you more time on it too if you need it. But anyway, what we need to do is need to write one variable in terms of the other. That's what we've done every problem so far. Instead of having an x and a y, we need just an x or just a y. And so that's where the constraints come in. Or in this case, the similar triangle thing. Are there questions about the Pythagorean theorem? Does that seem okay? I'm gonna zoom out a little bit so we can maybe keep looking at this. Why wouldn't it zoom out? I'm having such a hard time with this today. Not going to be able to zoom out? Okay, that's fine. So using similar triangles, similar triangle property above, looking at the picture, tells us, remember, E to A equals B to D. So that would be 6 is to X as Y is to X plus 6. Let me write that down. Let me do it in the same way. So I'm going to use this property on this triangle, right? So E is side 6, A is side X, B is side Y, D is X plus 6, right? So we end up with this relationship. 6 is to X as Y is to X plus 6. And that's helpful because that's how we can relate X and Y. Right? We can solve for Y in terms of X or vice versa. Right? In other words, you could multiply the X plus 6 and get Y equals 6 times X plus 6 over X, which is 6 plus 36 over X. And so you can sub into the L equation. Right, this thing is going to go into the Y. And so really what we want to do is you want to find the min of L equals 6 plus 36 over X squared. I've got a pretty crucial error on my screen right now that I just caught, but anyone thinking that I wrote something down wrong? Usually I feel like someone might catch that. Did I do the Pythagorean theorem right? That's what I'm looking at. So in the Pythagorean theorem, a squared plus b squared equals c squared, right? So this L needs a square on it. Everyone see this? I don't know if you can see that. See this thing I just added, the square? Right, a squared plus b squared equals c squared. I forgot the c squared part. And so that also needs to go right here on the last part, which means the thing we're really trying to minimize is the square root of that. So find the min of L equals square root of that nasty thing. Questions about the setup? Anything? I hope that's not just so confusing that you don't have a question, but I'm happy to wait. In fact, I will wait, let people catch up, and then I will say one more thing, and maybe we can look at the quiz. Anything here at all? The only other thing I was going to just finish with on this problem was just, I'm not going to find them in, you can do that, but let's talk about how you do that, right? How do you, so find them in, you're going to set L prime equal to 0, etc., right? But how do you take the derivative of that thing? What is this going to end up being? Like how should we set up this derivative? What kind of rule is it? So what rule? It's a chain rule. Sebastian, I see your question. I'll clarify that in a second. So L prime is a chain rule with the inside function, I'm sorry, the outside function being the square root, or x to the 1/2, right? And the inside function being what's inside there. And so to the point or the question before, if you want to do the derivative here, you could either square this out and use the power rule, or it's two chain rules. Whatever you want to do. I'm going to clarify Sebastian's question in a second here, but you'll feel like they can finish this one. What do you think? So Sebastian's question was, where do we get 6 over x? So we're doing similar triangle stuff. So we're doing this idea. Change my color here. We're doing this idea, right? So I did E is to A as B is to D. That's what I did in this situation, right? So I like compared the two right sides, or sorry, I compared the right side to the bottom side in the big and the small triangles. And so that's the same thing that's going on in this example, 6 over x, with our picture. Let me redraw the picture right here. Maybe that would be helpful. So our picture looks like this, where we had 6x, is that right? No, the other way. We had an x and a 6, and then the whole thing was x plus 6. This is y. And so that led to these things. God, I mislabeled it again though. Those x's and the 6 need to be switched. So it's a similar triangle thing, Sebastian. There's this thing right here that I was trying to explain. Let me know if I can say something more about that. Other thoughts at all from anyone?
Where did the x go?
Where did the x go and what?
And 6x cancel over x equals y over x plus 6.
So we solved this equation for y, which became this. And then that simplified into this. Like, is that your question? Like, how did it go from here to here?
But I still don't understand where the x went.
I guess I'm not clear about what you mean by where x went. X is right here. There's an x.
Never mind.
Right? If you want to know the algebra behind that, let's take a look. So we have y equals 6x plus 6. You can distribute the 6, and then you break it up into 2 fractions. These cancel, and you get this.
Okay.
There's really no need necessarily to do that. I just had them do that algebra when I was working on this one earlier. Other things you can clarify? I'm pretty confident that a couple people who have been emailing me probably can finish this now. I'm somewhat concerned about just how many people hadn't started it yet and whether or not they're now feeling overwhelmed. So I don't know what else to say other than it'd be great if you looked at the homework a little earlier and asked some questions and stuff like others. But anyway, let me know if you want to extend it is what I'm trying to say. It looks like I'm concerned about people finishing it tonight. Need some more time. Let me know. Other thoughts? Anything there? So I'm going to take all these files and put it into the homework file in the drive. Can I clarify anything else for anyone? All right, I'm going to start handing out the quiz in class. If people who are going to take that remotely would get set up, i.e. with their cameras on, and also be prepared to scan a PDF. I'm getting, just to be perfectly honest, I need people to stop sending me pictures. Spent class time getting everyone to learn how to create PDFs. I need anyone who's taking this quiz remotely to create and send me a PDF with your response. All right. Let me know when you guys are ready. Half the people online are still not ready, so I'm just out. Everything on this quiz is about visual representation of derivatives as they relate to the picture. And so you want to have that stuff out. All right, Sebastian, Tayshawn, not sure what's going on there, but you're holding everyone up in this chat. So I will go ahead and email it to the people who are ready. I really need to stop doing this remote stuff, guys. I can't handle it much longer. It's hard on you, and then ask people to do simple things and just get like stonewall responses. Really frustrating. 2, 4, 5, 2, 4, 5 people are ready. Here it comes. All right, coming via email, folks. So just to clarify what I'm asking you to do, now that everyone's had a chance to look at it, you know, on that first part, I'm just asking you to like circle places where, you know, the first or the second derivative is positive or negative, and then just drawing a star on the graph. So you literally just circle places that are positive or negative, and then just drawing a star right on that picture. And then in the table, I'm trying to make that look like one of the homework problems, where I'm asking you to fill in the table, and then you have the options that are listed in the options section, right? So like the first column should be either increasing, decreasing, constant. The second column should be greater than 0, less than 0, equals 0. The third column is increasing, decreasing, constant, etc. Let me know if you want me to clarify anything. The third, oh yeah, that third column, thank you. That third column should be the first derivative, should be a first derivative. I'm sorry about that. Let me be sure that that's what I'm thinking about. Oh gosh, of course this happened. No, the third, they're all correct. So the third column should be the derivative. Right, so the second derivative tells you how the first derivative is changing. That's how you want to think about the third column. The second derivative tells you how the first derivative is changing. Thank you.
Dr. Levy? I finished up. I'm about to give another 2, but it's about to be a PDF and all that. So we straight. Thank you. Have a great rest of your day.
Take care.